is simply because we have multiplied this number here with 52, because there would be 52 possible cards for that, and that's why we have 0.5668 bits. And the unit for Shannon's entropy is bits, and the highest value of entropy is 1. So you take note that highest value of entropy is 1. And you should know that when the probability is high, then the entropy is low. And if the probability is low, then the entropy is high. So this value here is considered low, right? That's 1 over 52. And this is considerably a high entropy. So that's the relationship that you should look out to. Another example would be still playing cards, is that consider calculating the entropy of a set of 52 playing cards if you only distinguish them based on their suit. So you have hearts, you have club, you have diamonds, and you have spade. So these are the possible values, right? So calculate the entropy for this, and you will be distinguishing that in terms of each of this. So what would happen here is let's start with H. These are called suits, and that the negative summation of L is an element of the heart, the club, the diamond, and the spade. I'm not sure why I'm drawing this. It's better to use letters. So yeah, bear with me. So you have suit equals L times log of 2 suit is equal to L. So let's just simplify this. Okay. So we would have, let's have this in brackets, probability that the suit is heart, let's just say H, times log of base 2 that the probability is H, or heart. Let's enclose that one. And since this is a summation, let's add everything up. Probability that it's a club times log of base 2, that probability it's a club, and then plus probability that it is a diamond times log of base 2, probability of it being a diamond, and another plus of probability of being a spade times log base 2 of probability of being a spade. So what we have here, we know that in a deck of cards, we have these 52 playing cards. There would be 13 of hearts, 13 of clubs, 13 of diamonds, and 13 of spades. So that is simply like this one. 4, because there are 4 of them, you have 13 over 52 times log base 2 of 13 over 52. So that is, if we calculate that one, calculate this times 4, and it has a negative number for sure because of the logarithmic, the answer would be what? One half, or 0.5 bits. So yeah, that's how we calculate for entropy. So now that we know how to solve for the entropy, let's jump into information gain. So I hope it was clear what entropy is. So basically, Shannon's model entropy is a measure of uncertainty or impurity. And we know that the high probability we have, the low entropy there is. And if there's low probability, the entropy is high, given that the highest value of entropy is always 1. So the range of entropy is 0 to 1. So for that, we will jump to information gain. I've written here the most important points. So information gain from, or IG, from the word information, it's a measure of informativeness. And it is also basically the measure of reduction in the overall entropy of a set of instances that is achieved by testing on a descriptive feature. So what this basically means is that it balances out the impurity. So we cannot solve information gain without solving entropy first. So um, while entropy is a measure of impurity or uncertainty, information gain is the measure of how informative it is, and its main goal is to reduce the overall entropy in an instance, and we test this on descriptive feature. So we will be this will be a lot clearer once we have an example. So there are 3 steps in computing IG. So number 1 is compute the Shannon's entropy, and then number 2 is compute the remainders, or REM. And number 3 is that entropy minus the remainder. And then that's when we will get the information gain. So we have a data set here. These are randomly taken from a large data set, and these points here are email spam prediction. So there were over 10,000 of this, and for the sake of manual solving, we will be taking only 6 of them here. And we have suspicious words, unknown sender, contains images, which is binary true or false, and we have class. So my question is, which one do you think is the target feature? So the target feature is class. This is the target feature. This is what we want to predict if it's a spam or a ham. So spam emails should be avoided or deleted. Ham is what we want. So these are what we called the descriptive features. And these instances have impurity on them, meaning they have entropy, right? So to solve for the information gain, take note or a screenshot for this. To To solve for the information gain, we will start with solving for entropy. So we will have step 1. To solve for the entropy, we know that it's H T such as in dataset equal to negative summation, such as L is an element of either spam or ham. Probability of T equals to L times log of base 2 probability of T equals to L. And that's the entropy. Now, what we need to do is get the summation of this. So the probability that the email is spam times log of base 2 that the probability is that the email is spam. So that's one part. And then we have the ham here. We have the spam, which is this, and we have the ham. So we have probability of T equals to ham times log of base 2, that probability is equal to T equals to ham. And yeah, that's that. So what we know is that, going back to the data set up, the probability that it is a spam is 1, 2, 3 over 6. So same for the ham, that's 3 over 6. So spam is 3 over 6. The probability of getting a spam and probability of getting a ham is also 3 over 6. So we have 3 over 6 times log of base 2, 3 over 6, and we know that this also has 3 over 6, so we just put outside times 2. Okay, so we have 2 times what? 3 over 6 times log of base 2, 3 over 6. That is negative 1/2 or positive 1. That's bit. 1 bit. So this is the highest number. It has a high entropy for this one. Now step 2, so we will note this as entropy is equal to 1 bit. Now what we will need to solve next is the remainder. So we have remainder of words in the dataset B. So absolute value of D words equals true over D times H, or entropy of T equals D words equals true. So this will be longer because we will need to get the remainder, or we should know that the remainder gives us a measure of information that remains required to organize the instances into pure sets after we have split them using a descriptive feature. So we have words, suspicious words, we get the remainder for this. After the words, we get the remainder of the sender or unknown sender, and contains images, we will need to take the remainder for that. So notice how these are all binary, categorical. This target feature is a categorical variable and binary, and these are also categorical and binary. Okay, so we will get the values for each descriptive feature for the remainder. So this would be, this is not finished yet. Sorry. So we have plus, oh, sorry. Plus d words is equal to false over d absolute value of d times h entropy that d words is equal to false. There are two possible values for them. This is a very good example for this solving information game because it's super easy to solve when we have binary categorical values for everything. So this is basically, if you check the data, how many true, you have true suspicious words it contains. If it's true, yes, the email contains suspicious words that they are tagging as suspicious words, and there are 3 as well for false. So this is similar to what we have earlier. This would be put this in such a way that we need to remember that we need to solve for the remainder depending on how many target features that we have. Not target features, but descriptive features that we have. So we need to solve for the remainder of suspicious words, remainder of the unknown sender, and remainder of images, suspicious images in the data set. So I'll show you the formula to be used for the suspicious words. So we should consider that suspicious words has 2 possible values, either true or false. So the formula for this would be absolute value that d words is equal to true divided by the data set for the words times the entropy that the target feature is, and the data set that suspicious words is equal to true. So note that there are 2 possible values for words, right? So we need to add the value of the second, where data set that words is equal to false divided by the data set for this times this one, the entropy that the words is equal to false. So yeah, you get that it's for the false. Oh, sorry. Let me just close that. So for the unknown sender and the images, the formula would be almost the same. Note that for the unknown sender, the possible values is also true or false. Contains images is also true or false. So you just need to change this to sender or change this to images in order to solve that. So I'm gonna show you how we should solve for this. So the remainder for suspicious words in the data set is D. So we will solve first for the first term. So it means that the data set we will be looking at is for those feature in words, descriptive feature, the suspicious words is equal to true. So we will only be looking at this data set right here. Only here. The first three, since these are the only suspicious words that is equal to true. Therefore, we have there are 3 suspicious words is equal to true over 6. 6 of them in total. 1, 2, 3, 4, 5, 6. Times the entropy, which is this one. So we should solve for the entropy. You should remember how to solve the entropy. The summation that the probability of the target feature equal to L times log base 2 of the probability that T is equal to L. And that is the entropy. Such that these probabilities is L is an element of the target feature which contains either ham or spam. Right? This is the target feature. Target, descriptive, and descriptive. So this is the T for target, such that L is an element of T, such that T it has either 2 possible values. Either the email is ham or spam. So spam are spam and ham aren't spam emails. So yeah, that's that. Now we will be solving for the second term. So this is again, we will be looking for the data set for which the suspicious words are all equal to false. Note that we will be looking at from 693 to 976. They are all false. So there are again 3 over 6 times the entropy. So this is summation of probability that T equals to L times log base 2 probability that T is equal to L, such that L is an element again of the target feature, which may consist ham or spam. Now we're ready to solve. So for the first term, we will have 3 over 6. I'll put that in a square bracket. I'll just move further here. 3 over 6 times the negative. I'll put that out. And now we have 3 over 3 times, no, not 3 over 3, but let's just think about this. So let's first see the values for true that is also has a target feature that is ham. So let's look at this. So we have true here and the target is ham. So how many ham target values has true values in suspicious words? So there are 0. 0, that is 0 over 3. So we will have 0 over 3 times log of base 2, 0 over 3. Plus, this is a summation, right? How about spam? For the data set is words is equal to true, we have 3 that is spam. Therefore, we have 3 over 3 times log base 2 3 over 3. And then here we will have for the second term, we have 3 over 6 times this is for when suspicious words are false. So there are 3 of them again. So we would write again 3 over 6, and then its entropy is similar. Let's say ham such that the words are false. So you can see here that these this is 3 over 3. So this is 3 over 3 times log of base 2, 3 over 3, and then plus, since this is a summation. How about spam such that the suspicious words is false? Do you see any spam here when the suspicious words is false? So we will have 0 over 3 times log of base 2, 0 over 3. So we will need to crash out every multiplied by 0. Therefore, we have this as 0. Sorry, we have this as 0 and this is 0. Oh, no, not that one. We already have 0 here and then 0 here, since 0 divided by any number is equal to 0. And we also know that the log of anything, the log of x of base 1, base x, log of 1 base x, no matter what base that is always equal to 0. We know that already, so yeah, this is 0 as well, because this is 1 and this is 1. So what we have is 3 over 6 times 0 plus 3 over 6 times 0. And that is 0 bit. So we should write remainder of words is words such in the data set is equal to 0 bits. I'm going to solve for the remainder for sender and images. So yeah, let's just compare our answers. I'll show my solutions in in the next seconds, and then yeah, you can double check from there. So this is for the words. Sorry, sender. So we have 0 bits for the words, and for the sender we have this answer right here, 0.918 bits. So it's pretty similar, not similar, but it's the same for the words up till this line here, for the second line, because they also have 3 over 6 and 3 over 6 for true and false. However, it differs when it's ham or spam. So you can see that focusing our attention in this descriptive feature we're looking at for all true first. We have 1, 2, and 3. So that's 3 over 6 in total. And to think that if it's ham, how many is that? If it's ham, that is true. That's 1. So I might have written it in a different way, but you can see right here that I have 1 over 3 here as well for ham. And how about if it's spam and it's true? So it should be 2 over 3. You can see it right here. So true and it's spam, we have 2 over 3. That's what we have here. 2 over 3 for spam. And yeah, you take the sum of these terms. You have negative 0.918, and with the negative here, that would make the logarithmic value be positive. Same happens for when it's false. So let's try first. If it's false, let's say we have x. We have 1, 2, 3 false. And how many of the target equals to spam is in false? So we have 1. We have 1 only. That's why we have 1 over 3 here for spam. How about for ham? That is false. We have 1, 2. So 2 over 3 all false. So we have these terms here for this ham. Yeah, that's for the remainder for the sender. So for the images, we should have the same results here, 1 bit. So the same, we should follow the how I solve the first 2 for this one. Now we will need to compile everything that we've solved. So this is to solve for the information gain. We're on step 3 of solving for the information gain. Step 3 is subtract the remaining entropy value from the remainder from the original entropy computed in like entropy, like H, so H of entropy of the given in the data set. So basically we have the information gain for words in data set is H of glass, the target feature, minus remainder words data set, which is this one is what we solved the class previously. We solved this already, and it is equal to 1 bit minus 0. We solved this earlier as well, so this is 1 bit. For information gain in sender, we have H class D minus remainder of sender D, and this is also equal to 1 minus the value for this we solved earlier, 0.918, equals 0.082 bits. And lastly, the information gain with regards to the images. So we have H class minus D minus remainder of images. This is basically 1 minus 1, so this is 0 bit. So the information gain for the words has the highest value. This is equivalent to the total entropy of the entire dataset. So this indicates that the feature is perfectly discriminatory with respect to the target feature. This means that when we want to predict the class or target, if you want to determine if the email is spam or ham, we should first look at the suspicious words as descriptive. So the contains images has an IG equal to 0. So this may be removed from the decision tree. It's up to you, but when information gain, we don't equal to 0, we don't gain information from that to predict the target. So yeah, we should start our decision tree with the suspicious words. This contributes to this discriminates the if it's either a spam or a ham.